All right, now we want to talk a little bit about how this method works, to go through some of the calculations that one would do. Obviously, we use computers to do the real calculations, but here's a very small example. But I think, although it's limited, I think it gives the essence of what this method is all about. So critical path method goes like this. Each task is identified and depicted by a node, either a box or a circle or something like that. As we've shown here, this is a very simple project. We're designing and installing a tank on a foundation, okay? So here are the tasks. Design the tank project, select the supplier, manufacture the components, etc., okay? And note, as I've said, we show each task within a node or a box. And then we connect the nodes in the order in which they'll be performed. So for example, the very first thing we do in the project is to design the tank project, after which we can do two things: select the supplier and construct the foundation. We've simplified it, of course, but I trust that that's okay. And now, once we've selected the supplier, two things can happen. We can manufacture the tank components by the supplier, and also we would expect the tank supplier to prepare installation drawings. So that's the sense of this, really very simple flow chart, okay? And then moving on, we manufacture the components, after which you ship them to the site, they get delivered. You can't assemble the tank until three things have happened. The foundation has been constructed, the installation drawings have been prepared, and the tank has been delivered. So then we assemble the tank once those three things have happened, and then finally we test and commission the tank, and that would be the final activity, the final task in the project. It's important to realize that in this model, we assume that all of that activity has to be done before anything following it can start. It's not that you get partway through and you can start what follows it. If that's not true, if, for example, for some reason you could start manufacturing the components before you'd selected the tank supplier, then we would have to complicate that some more, so it in phases and so forth. But I think, again, this gives kind of the essence of what this is all about at this stage. Having constructed the network and agreed, hopefully, among the project team that this is the way we're going to try it, then we will estimate the duration of each activity, of each task, okay? So let's just do that. We will select and what does that depend on? Well, it depends on basically the work that has to be done in the task, the resources that you're going to apply to it, the kinds of equipment, if it's an outdoor activity, what you estimate the weather to be, whether you're going to work overtime, et cetera, double shifting and so forth. We'll just put in some numbers here to demonstrate here. So let's suppose, and these durations will be in days, okay? So let's just put in here 10 days for designing the project, 8 days for selecting the supplier, 10 days for manufacturing the components, and 4 days to deliver it to the job site. Let's suppose it's going to take 25 days to construct the foundation, 3 days to prepare the installation drawings, 15 days to assemble the tank, and 4 days to do the testing, okay? So we have an initial activity, designing it, then we work all the way through to the final activity, testing and commissioning it, after which we consider the project to be complete. Okay, now what's this about critical path? Well, what we're trying to do is determine how long, based on these estimates, based on the sequences, how long this project is going to take. So, some very simple calculations to help us do that. We define four parameters, if you will. We define something called an early start, the earliest that the activity or the task can start, and the earliest it can finish, based on the preceding activities, the predecessor activities, based on what has to come prior to that activity. We also define the latest that it can start, late start, the latest it can finish, based on the end date. When do you want to finish it? Then you work backwards to determine the latest times that each of these activities must start in order to meet that. And I'll show you what that means, I hope. Okay, so we start at the beginning. we say the project begins at time 0, the beginning of the first day, if you will. And so we write a 0 here. That's the early start for this first task. And if it starts at time 0 and takes 10 days, then the earliest that it can finish is 10. Couldn't be simpler, okay? Now that early finish for this predecessor activity, the predecessor for these two activities, determines the early start for these two. So if this finishes, if it can finish at time 10, that means selecting the supplier can start at time 10, as can the activity, the task constructing the tank foundation. And we just go on like that. 10 and 8 is 18. 10 and 25 is 35. Makes sense? Sure does. Okay. For the manufactured tank components, 18, 28. This would be 18. The earliest it can start at 3 is 21. Deliver the components can start at 28 and take 4, which is 32. Assemble the tank. Now it gets complicated relatively, because what is the earliest we could start assembling the tank? Well, it depends on this one, and this one. But it has to be the latest of those, because all 3 of those must be completed before we can start this. So we would compare 35 and 21 and 32 and choose 35. Okay? So if you want a rule, it is the early start of any activity, except for the beginning one, is the latest of the activity's immediate predecessor's early finishes. Okay? It's the latest of the immediate predecessor's early finishes, because those predecessor activities have to be finished before you can start this next activity. Okay? Okay, given that 35 and 15 is 50, which means we could start testing and commissioning at time 50, and the project based on this could be finished as early as 54 days. That's half of it. And sometimes we call that the forward pass. I know this is football country, and so call that the forward pass. Now the question is, what is the latest that each activity must start and finish in order to get this project done in 54 days? Okay? Well, the answer depends on what we assign as the latest finish for the last activity. Is there a contractual obligation to finish it at time 60, for example? Or does the boss want it in 50? What we usually do for the initial pass is to say, well, we know it can be done in 54. Let's use that as the project completion date, time, okay? And we'll assign as the late finish for the last activity its early finish. So we're saying we're targeting to finish this thing in 54 days. Okay? And so now we'll work backwards to find out how much, or at what point each of the activities must start and finish in order to get done in 54. Okay? 54 minus 4 is 50. Fairly straightforward. You got to start that at time 50 in order to get done in 54. And then working backwards, that means that we have to finish assembling the tank at time 50, which means it must start at time 35. Okay. Now we work backwards from there, so that the latest that deliver the tank can finish, must finish, is 35. Otherwise, if it's later than that, it's going to push everything later. So 35 for the finish minus 4 gives 31 when that one must start. Working back to these installation drawings, it's got to be finished by 35. So must start by 32. And then back to this, construct the foundation. Must finish by 35, therefore must start by time 10. Manufacturing the components, we have to start the delivery by 31. Therefore, they must be finished by 31. and therefore they must be started by 21, the manufacturer, because it's a 10-day activity, task, okay? Okay, now finally, we get a little more complication here. When must we finish selecting the supplier? It's either by time 21 because of this one, or it's by time 32 because of this one, okay? And the answer is the smaller of those two numbers, okay? We have to finish this by time 21, not because of this drawing activity, but because of the manufacturer. Okay? If this were to slip as late as time 32, it would not impact this one, but it would impact this one badly. If it slips 30, out to 32, then we're going to push this whole sequence too late. Okay? So the rule on that, if you want a rule, is that for any activity's late finish, we select the smallest of its immediate successors' late starts. Therefore, we choose 21 instead of 32. Now we continue to work backwards. 21 minus 8 is 13. This is 35 minus 10 that we've already done, minus 25 equals 10, which you've already done. And then finally, we come back here, applying our rule again. The latest finish for design tank project is either 13 or 10. We select the smaller of those two, and we take 10 and we subtract the duration 10, and we get 0. So what does that say? Well, the first thing we can conclude is that we must start the project at time 0 in order to finish in 54 days, which that makes sense, okay? Now, we note that some of the activities have their early starts equaling their late starts, which is also to say they have their early finishes equaling their late finishes, okay? And let's go through and identify those tasks in the project. Well, it's this one, 0 equals 0 or 10 equals 0, so we're going to mark that. And we're going to call that a critical activity. That activity has no variability in the way it can be scheduled based on all of our assumptions here, okay? It can't slip. It's got to start at time 0. It can't start any earlier than time 0, so that's critical. And then let's look for some others. Well, the same is true here. The construction of the foundation, the assembly of the tank, 35. It can't start any earlier than 35 because of its predecessor activities. It must start by 35 in order to meet our 54-day completion time. So that's a critical activity. And then finally, testing and commissioning the tank, the same thing. So what we've marked here is a sequence of activities, start at the beginning and work through to the end of the project, okay? And they're connected, and we're gonna heavy up the connector here, okay? And we call that the critical path, okay? If we add their durations, 10 and 25 is 35, and 15 is 50, and 4 is 54. That is our project duration. So that is the sequence of activities responsible for determining the total project duration. And as we said in the first part of this, that means that these are the activities that have to be supervised most closely. If any one of those slips by starting too late or by taking longer than estimated, and if we don't do anything about that in subsequent activities, if they stay the same, then we're going to expect a slippage in the project end date. Okay? And the other part of that is that if we want to take some time out of this project, suppose the word is we got to finish in 50 days. Well, it's to this critical path that we look to take time out. It can be a little trickier than that because you might squeeze the critical path so much that some other path becomes critical. But at least initially, we would look to the critical path to take time out. If we want to take 2 days out of this project, then doing the manufacture part in 8 days instead of 10 will have absolutely no impact on the total project duration because it's not critical. If you want to take 2 days out, you better try to construct the foundation in 23 days instead of 25, for example. So that's the sense in which we identify this thing called the critical path. The other activities, the other tasks, have some variability in the way they can be scheduled. For example, selecting the tank supplier. What this tells us is that we could begin that activity as late as time 13, if it takes 8 days, and finish it by time 21. And that would be okay relative to the total project duration. If nothing else changed, then it could slip by 3 days and we would not impact the total project duration. Granted, it would push these successor activities ahead, but that's okay as long as all you're trying to do is maintain your 54-day project duration. So we define one other parameter here, which I've shown in my legend here. We call that slack. Slack is the amount of time that an activity or a task can slip beyond its early time without impacting the overall project duration. And that is calculated by taking the late start minus the early start, or the late finish minus the early finish. And in this case, the answer is 3. So we'll write that in there, and we call that slack. An older term is float, means the same thing. Here we have 21 minus 18, that's 3 for the slack. 31 minus 28 is 3. Prepare the installation drawings. 32 minus 18, which is 14 days. We have a lot of variability in that activity. It could take an extra 14 days, or it could start 14 days later than 18. And again, it would not impact the total project duration. The critical activities, guess what? They have 0 slack. It's sort of the same thing as saying they can't be changed from their original schedules. So 35 minus 35 is 0, 50 minus 50 is 0, and there we have it. Now, one caution on that, and that is this activity has 3 days slack, this has 3 days slack, this has 3 days slack. But remember, we define that slack as the amount that an activity can slip beyond its early time without impacting the total project duration. The caution is, we can't say this has 3 days slack and this has 3 days slack and this has 3 days slack, and therefore add those slacks together and claim that we have 9 days slack along this subpath here. That's not true. We only have 3. But again, one more time, the slack is the amount that an activity can slip beyond its early time without impacting the total project duration. Not that it might not impact some of the successor activities in its path here. So that's the essence. Obviously, we do it by hand with a small example, but the computer is going to do that for you very rapidly and without error. That really completes the very rudimentary explanation of how this method works.